Thank you, everyone. So I'm Amitay.
I'm
Martin, and we are the CTDB guys. We are Samba team members, and we work at IBM Oz Labs in Canberra. Now, as many of you may be aware, may not be aware, CTDB is part of the Samba project. Samba project, which was started by Andrew Tridgell. He wanted to find out if there is a way to talk to Windows machines so he can access files. And that's the story 20 years ago. 20 years passed. Samba has grown. It does lots of things, including file serving, Active Directory, so on and so forth. But for this talk, we are going to focus on the file server aspect of it, and specifically the clustered file server, which is clustered Samba. So that's where CTDB comes in. Okay, so you probably know how Samba works, but this is just a short cartoon to illustrate what it is. In the Windows world, Windows uses SMB protocol to communicate between the client and the server. So we replace the Windows server with the Samba server. Everything still works. And today you know that there are many other operating systems which talk to Samba server using SMB protocol. So that's just a brief about what we are interested in. So how does CTDB fit into this picture? Okay, so now let's say we want to start clustering this Samba. Okay, now the key component of clustering is figuring out where Samba stores its data. Now, if you look at the Samba instance running on one of the servers, so Samba creates lots of databases. Those are TDB databases, trivial databases. Again, TDB was actually written specifically for Samba. Now, it stores lots of different types of metadata, including what are the active sessions, number of open files, logs, even registry, things like that. So far, so good. So let's add one more Samba server. Okay, so now we have two Samba servers with their individual databases. Okay, so each one has its own copy. Now somehow we have to make sure that these databases work together. So that's what the clustering is all about. And that's where CTDB comes in. It tries to manage these databases across the whole cluster, across different nodes, and provide a single database view for each Samba instance running on a node. Now, remember here that Samba doesn't do any clustering specific thing. So Samba is running as if it's a standalone server. It still talks to its databases on a local node, on a local machine, but it sort of interfaces to CTDB in some fashion. And that helps us to create a cluster of Samba without actually changing a lot of code in Samba itself. So in future, if you have any application which uses TDB to store its state or metadata, you can potentially benefit from using CTDB just to cluster your application. Okay, so what is CTDB made up of? Three important libraries or three important components. One is the talloc, which is the dynamic memory manager. It's hierarchical and it simplifies a lot of memory management tasks in CTDB. Tevent, which is the event handling framework. Again, this was also developed specifically for Samba. All the three components were developed specifically for Samba. So tevent is really the crucial part of CTDB, which gives us the asynchronous event handling and makes it really perform really well. And of course, there is TDB, which is a file-based database. Okay, so as I mentioned, CTDB was designed to be high performance because we want the, if you are using a single instance of Samba server, then it's very fast when it's trying to access the databases locally. Now we want to make sure that it can still do that in a clustered environment. So care has been taken to design certain protocols so that as far as possible, it tries to access local databases, Only when there are some records which are common or which are contended, in which case those records need to be migrated. So most of the time, CTDB doesn't get involved if you are using fairly normal load. CTDB doesn't have to do too much work. But once you start really loading the system with hundreds and thousands of SMB connections, well, that's where the CTDB really starts doing work. Again, important issue, the daemon is completely non-blocking. So in the main daemon, we don't do anything, any operation which can block for indefinite amount of time. If such a task happens, I mean, if you need to do something, then we fork a child and let the child do the blocking work. Well, in addition to providing database features, CTDB does a lot more. It supports service monitoring, it does IP allocation, and so on and so forth. So that brings us to the talk today. We are going to really talk about the bugs which we have seen or encountered while doing integration testing and doing performance analysis. So we really wanted to benchmark CTDB to, or rather clustered Samba, to figure out how much can we stress the system, the clustered Samba system, and how much performance can we get out of it. So let's get to the first defect. So we have two kinds of defects. One is the performance defects, and there are some which are really bugs or bugs. So when we are running Samba under load, we notice that CTDB daemon starts responding very slowly. Okay, that's pretty vague. So let's start looking at how do we figure out what's happening. So there are many ways which you can start looking at it. One of the ways, a simple way, is to look at, okay, how many connections do we have? So that's what we did. So we tried to find out, this is a 4-node cluster. So we look at, okay, let's see how many connections there are. And CTDB uses port 4379 TCP. So we grep for all that. And so do you notice anything? The normal connections. Yes, so you can see that there is a large receive queue. So you can see lots of bytes in the receive queue in all the active connections. So that brings the question, how does CTDB read packets from the socket? Now, this is one part. You could also do strace. So when we ran strace on the same under same conditions, we find that daemon is running lots of read calls. So I'll come to that. Now, before we go into explanation of it, one place where, as I mentioned, CTDB creates a child So when CTDB wants to read anything from the socket, it uses tevent library to register a callback function, because everything is done asynchronously in the library. So we have a function called qio_read, so whenever a particular socket there is any activity, there is data in the socket, this function gets called. So first we check how many bytes there are in the socket buffer. Then we read the actual packet size. Now here in this case it happens to be 4 bytes. So first we read 4 bytes, assuming there are adequate number of bytes in the buffer. And then we actually read those many bytes, depending on, again, how many bytes are there in the buffer. And then we call a function which processes that packet. So is there a problem? Yes. So to read one packet, it is using 2 read system calls. Okay, so that's what we see when we run strace, that it's taking too much time or spending too much time just trying to read the packet. So we simplify this. So we still find out how many bytes there are. But now, instead of just reading bits and pieces, just read the whole buffer. Whatever is there in the socket buffer, just read everything, and then process all that buffer as many number of packets. So this gives us a definite improvement. Now we can do multiple packets in one read system call. And just to see what the queue process does, well, you do the same thing. You sort of figure out what is the packet size, you extract it in a separate buffer, and then you call the function which processes that packet. And since we want to process all the packets in the buffer, you sort of create an event which says, okay, once this function is done, come back and process another packet. The reason why we have to do it this way is because when you're processing a particular packet, the connection might get closed or whatever, in which case all the state is freed. So we don't have to, so we can't just call queue process function directly. So that brings the question, what happens if you get 1 million packets in a buffer? So which means CTDB will just spin processing 1 million packets. So obviously this is not the ideal solution. This is just one of the improvements. So then we had to actually limit the size of buffer so that it processes certain number of packets and then it goes and looks at other sockets. So it sort of becomes fair across multiple sockets which are open. Okay.
Okay, so Amitay is the performance guy, and I'm the crazy bug guy. So CTDB stop is a command that administratively takes a node out of the cluster. It makes it inactive. And we would just see the CTDB stop command time out in our tests. We run tests every night. CTDB stop just times out. So we can run a really simple test. So there's a special node in CTDB called the recovery master, and for this talk we don't care what that is, but we can ask CTDB which node it is. In this case it's node 3, and then because it's node 3 we say do CTDB stop on node 3. And to tickle the bug, we run these in a loop with a variable and with a CTDB continue, but you don't want to see that. And after about 10 or 20 iterations, we hit the bug. We get a timeout. Now, the CTDB command has a 2-minute timeout to catch endless loops. And because some of the error handling is a little bit shoddy, and we can't tell the difference sometimes between a temporary failure and a permanent failure, we just spin forever, keeping on retrying things. And that's why we're seeing 2 minutes here. So that's really no surprise. So here's the CTDB stop code, or obviously a cut down version of it. First of all, there's a loop at the top that just checks if the flag that a node is stopped is set. Keeps trying to set it. Is it set? When it is finally set, the loop terminates. Now, are we getting stuck here? Well, we can exclude it by printing a message and doing really dumb debugging, and that works. So we actually get to that point. So what happens in the IP reallocate code below? You don't need to know what all this stuff means, you just need to admire the shape of the code. So the IP reallocate code, first of all, it registers a message handler, because it's going to send a message to the server and it wants to know when the reply comes. And that handler is going to set IP reallocate finished to true. So we initialize it to false, register the handler, and then we really start doing things. Then we ask which node is the recovery master. And we get an answer. Then we ask the recovery master to do one of these takeover runs or IP reallocates. And what could possibly go wrong? Well, one thing is that if you send that message to a node that isn't the recovery master, it'll ignore the request. So, if we send the request to the wrong node, we get absolutely no reply. And why would a request go to the wrong node?
Because the one that's trying to shut down is the recovery master.
And stop isn't actually a shutdown, it's just kind of a quiesce, but you are in fact correct. When we ask all the nodes who's the recovery master, it's a zero-based node 0, 1, 2, 3 has the wrong idea. So when we tried to stop CTDB, we sent the request to the wrong node to do the IP reallocation. That's bad. Inactive nodes can't always identify the recovery master, and it turns out to be a pretty simple bug. But you know, it sat there for ages because we kind of just went, we've got bigger fish to fry, or tofu burgers to cook. So how do you fix this? Well, that's pretty simple. Instead of asking who the recovery master is, since you're only going to get a reply from the recovery master, you just broadcast. And that's a really nice thing to do in a clustered environment. You don't ask questions for which you're not sure of the answer or for which the answer might change. So broadcast is really good here.
What if you get two answers?
There are two answers to that. One is that that's fine because you only want one because you're only setting a true-false flag, and you'll terminate. But if both answers come from the wrong node, it's imperfect, but you can't have. Yeah, we've got a recovery lock. You can't have two nodes that think they're the recovery master. However, a bug that you're not seeing today, you can have no nodes that think they're the recovery master until about 2 months ago. Okay, time travel. Time travel is always fun. Somebody decided to do a time robustness test on CTDB and, well, the whole clustered Samba setup that we're involved in developing for. And the sensible thing to do when you're testing whether everything is robust with respect to NTP time updates is to set the clock forward 10 years and then set it back again, because NTP does that never. Okay. So the CTDB script status command tells us when the last monitor loop was run. And in this particular case, the last monitor loop was run at about 5 o'clock in the afternoon, and getting on to 6:30 right now. We haven't run a monitor event for over an hour, and they're supposed to run every 15 seconds. And when we were looking at this, we didn't really know how CTDB used tevent, and this is what taught us. So, the crux of the monitor code is to run a bunch of scripts and kick them off asynchronously, register a callback that gets run when the script's complete, and then when the callback gets called, when the scripts have either run or timed out, we do a bunch of stuff, but then we also schedule the next monitor event. And I'm guessing in event programming, this is probably a very standard way of doing things. There's no regular timer that's just going off that we're attaching something to. We run one, we run the next, we schedule the next one. We run one, we schedule the next. So repeated events, each one schedules the next. CTDB uses tevent, as already discussed, and events are scheduled at absolute times. So when I want to schedule the next monitor event, I'm going to go forward in time right now to what will it be, 2024. I'm going to schedule an event 15 seconds out, and then I'm going to come back, schedule it.
In 15 seconds, it'll actually
Right. Yeah, I'm going to sit down, have a drink, and I'm going to wait 10 years for that timer to go off. How do you fix this? The fix is actually really, really simple. You travel forward 10 years in time, and by that time, relative event handling will have been implemented in tevent, and all of our problems will be solved. Yes, that was discussed, and again, bigger fish to fry because they're testing NTP robustness here, and not a very good test. So we just said test bad. Yes.
Why don't you just schedule 2 events at the same time?
Why don't we
One for the callback and one for the next event. You don't have to wait till the script finishes. The callback doesn't have to be done.
The scripts can take a while. So
it's not actually executing every 15 seconds. It's
correct.
Script execution time plus 15 seconds.
Correct. And so the scripts can also time out. And if we hit our timeout, then we'll also call the callback, and it will handle the timeout. Yep. Yeah, you'll still be scheduled. At some point, you'll still schedule something 10 years into the future. Yes.
Is it possible to find out when the next event is scheduled and say if that
is it, so the question is it possible to check what events are scheduled and, you know, maybe check the furthest away one and see if it's at a stupid time? That would actually be quite easy.
Not the furthest away, just the next one.
No, the furthest away is easier. Yes. Yep. There are many fixes, but you know, there are many fixes, but at the moment we've got bigger fish to fry.
So back to performance. So once we sort of fixed some small issues like the one which you saw before, we really started stress testing the box with 5,000 active SMB connections. So what happened? As soon as it reached about 5,000, the node completely crashed. Okay, that's not good. So we captured the crash dump and started looking at it. And okay, so one of the things we discovered was, oops, it's using all its RAM. So obviously it's invoking out of memory, and somehow it's not able to recover. So sort of something is happening which is just its kernel is not able to recover and it just crashes. So what's running in the system at that time? Okay, so let's look at all the process lists, sort them. Aha. Now we are running obviously 5,000 connections, so we expect 4,000, 5,000 SMB processes, and then related connection main, which is a plugin in Samba, but that's fine. But why do we have 1,200 CTDB processes?
Lots of children.
Yes, so there are lots of children, and so there is one special case where we really want to create lots of children, is when we want to get a lock on a particular record. Now, as I said, that we are trying to manage databases across multiple nodes. So the way each record is handled is each record has a location master and a data master. So whichever node is the data master that actually holds the record, and if on a node which is not a data master, we want a particular record, we have to migrate that record off. Now, if we cannot, so let's say CTDB is interested in trying to migrate a particular record, and it first tries to get a lock using non-blocking method. It says, oh, I can't get a lock. So it says, okay, I'll fire off a child process and let that handle the blocking call. So the child will actually block and just wait. Once it gets a lock, then it will tell the parent CTDB process saying, I got a lock, so do something with it. So let's look at the code which actually does this. So it's the CTDB lock wait. So as you see, there is a wrapper for fork. So we fork a child, then in the child process, we actually block on a TDB chain lock call, which is basically locking that record. Once the chain lock returns, we write the result that, which is just indicating to the parent process on a pipe between the child and the parent that we got a lock. And in the parent process, we have registered this pipe with tevent saying that, okay, if we have any data on this pipe, so call the function which will handle, which will actually do something. It doesn't matter really. It's and then there is a check so that we don't really do a fork bomb, that if we get more than 200 such requests which are going to be blocking, then if there are already 200 requests, then we queue the new request, and only when one of the child has finished, then we'll schedule the next one. Right. So this explains the number of processes, but it doesn't explain why we are running out of memory. So, okay, so bit of thinking about why we would be running out of memory. So obviously fork is not going to copy the process immediately. It's copy on write. So then we looked at so while the system was running, as is building the number of connections, we started looking at the memory info, little more detail as to where the memory is going, and then we notice that it's using large amount of memory in page tables. So even though fork is not copying the actual process memory, it's still copying the page tables, and we are actually overflowing the page tables. So, okay, we want to use vfork. So how does fork compare to vfork? Well, just wrote a sample program to see, and here are the results. So depending on how much memory is allocated in the process, when you actually do a fork or vfork, it takes different amount of time. So when you're doing a fork, if you don't have any memory allocated, so just a simple program, fork, and do something, it's very, very fast. It just takes about 40 microseconds on that particular hardware. But if you start allocating more memory and then trying to do a fork, then it starts taking more and more memory. And we are seeing about 2 to 3 milliseconds per fork on our system. So obviously, vfork has a benefit here. It's more or less constant. So replace fork with vfork. So now this is how the code looks. So only thing is with vfork, you cannot use the, you have to do an exec. So we create a lightweight helper process which actually obtains the lock. Okay, so far so good. So this stopped the node from crashing. But then we hit a next problem. Now CTDB started consuming 100% of CPU. Now CTDB is a single-threaded application, so it runs on single CPU. So it's running on one CPU at 100%. Okay, so what's happening? So now we have to figure out what's going on in the system. So we use perf. So we record the snapshot for about 60 seconds and then see what it reports. And there we can see that it's, now this is, the perf snapshot is recorded across multiple CPUs. So 15% really corresponds to 100% on one CPU. So, and during that entire time, it's really doing, spinning in one function. So what does this function do? It's a very simple function. So given message IDs, it's trying to find in a linked list. And if it is found, then it's just to check whether the ID exists or not. So why should this take a lot of time? Well, it's a linked list, and when we were earlier running the code, we didn't have so many message IDs, because every time Samba each instance of Samba registers a few message IDs, and then the list becomes longer and longer and longer. So solution, simple, just replace the linked list with a hash table, and immediately we solve that problem. And then we hit the next bottleneck. So this time from tevent library, similar story. So tevent, when you add a timed event, you talked about timer events. So it is maintained in a linked list in a sorted order of time. Okay, so the timers which are expiring sooner, they are at the top of at the front of the list, and which are further away, they're at the tail of the list. And since most common use is to schedule future events, as in Samba does, you start searching the list from the end, so where to insert this new event. Now, what CTDB does is it schedules lots of immediate events with 0 time. That means every time you insert a immediate event, it has to traverse the entire list, because now we are searching from the end, and then insert. So this was fixed by just keeping a pointer to last 0 time while entry, and we get over that bottleneck. So these bottlenecks really helped us to improve the performance. Then the CPU usage dropped to about less than 50% on average.
Yeah, so the amazing thing about that performance analysis is that with perf, anyone here could do that, right? You know, it tells you what function the problem's in. So none of that was rocket science. I think the next 2 bugs here are rocket science. So we've got the CTDB shutdown command, and it's meant to shut down CTDB. So what goes wrong? We do CTDB shutdown. We run CTDB ping, and it says, yep, still there. We wait 30 seconds. We ping it again. Still here. Oops. So when we look in the logs, yeah, the message got there. It started shutting down. It got up to somewhere, but it never finished. So here's the shutdown sequence. Just for your collective memory, one of the important things that happens is that monitoring is stopped. Then we run the shutdown event scripts, which are just a bunch of housekeeping scripts. You know, they shut down Samba. They do a bunch of useful things.
Monitoring being the timeout monitor.
Monitoring here is health checking of services, like checking that something is actually listening on the Samba port, checking that all the interfaces we expect to be there are actually there, and that they're up. They have link. Okay, so this is where we get stuck. We get stuck running some scripts. Is there a problem in a script or whatever? Let's find out. How are the scripts run? Okay, so the first thing we do when we're running the script is we launch the scripts asynchronously, like we do with everything here. Everything's asynchronous. Then we set the done flag to false, because we're not done, are we? Then we spin until done gets set. How does done get set? Well, that's pretty obvious. We've got the event script callback that gets run when the scripts are finished. And the most important thing it does for us is set done to true. Congratulations, sir, you have just spotted the bug. So why isn't event script callback being run? You know, there must be some reason for this. And, you know, we beat our heads against desks for a long time thinking, why isn't the callback being run? If the callback gets run, we terminate. Well, it is being run. It's being called. It's being run the first time when we're still in that code. Okay? The callback gets run, it sets done to true. We come out, we set done to false. And we spin forever. Now, of course, if this were expected, this wouldn't be a bug. So there's something unexpected going on in this CTDB event script callback v function. We spin forever. Okay, the two things of relevance in this very big function is that we set up a bunch of state, including setting up the callback. Then we cancel the monitor event. A lot of the events that we run in CTDB can interfere with monitoring. You know, we might restart a service, whatever. So while we're running another event, if monitoring is running, we want it to go away for a while. So we cancel it. And that's, you know, that's part of the monitor cancellation code, the exciting part. Now, remember way back on about the first slide of this, we stopped monitoring. Well, what that did, you can see this current monitor pointer here. There's a callback in that structure. It's the same sort of structure we're talking about here. Well, the callback there got cancelled and freed, and we've got a dangling callback pointer. It's just hanging out there. And the new callback structure gets allocated at exactly the same place. So it gets run and freed there, the first time we call this function, during the monitor cancellation, and hence the calling code spins forever.
How long did it take?
It took us about 3 hours of dedicated debugging. For some reason, we couldn't find some things going on in GDB, and we resorted to printfs. And then I really wanted to show you this one today, and we were trying to understand how it worked, and we had to relive the whole thing because I kept on going down the path of why isn't the callback being run? The only way we can't terminate is if the callback isn't run, but it is. So the fix is just to do things in a different order here. Now, those who are really observant might spot some potential problems, but I can assure you that none of those occur. Yeah. Okay, yes?
How set done to false before you set up a callback. In a multi-programming environment, you can say that we have a race condition there, and I know you said this is a single-threaded program.
Okay, let me try to multitask and think about it. So the question is, why don't we set done to false before we call that initial function? We can
do that, but that really doesn't solve the actual underlying problem.
Sure.
Yeah, so that just
right,
gets
thank
over
you,
the
yes.
original.
As a matter of fact, it's double free. Unless you fix the original cleaning of the monitor to actually know the pointer.
That's the potential problem that I didn't mention. And no, we do a pointer comparison before we check that a pointer is in the list of registered callbacks.
You still need to fix the original bug of leaving the dangling pointer.
Doesn't hurt. No, it doesn't. We never double free because we check that all the callback structures are registered in a list, and freeing it removes it from the list the first time. So yes, we have a dangling pointer. We should probably null it, but
Race condition, need to check twice and both of them see it's there and both free it, or is that impossible somehow?
Yeah, it's not multi-threaded, it's just single-threaded, so that doesn't happen.
yeah. Anyway,
There are lots of race conditions, but not this one.
You have callbacks, they have the potential for something kind of weak that you was not.
Yeah.
Shouldn't you print out an error message if you try and do a double free?
Yeah, if you try to double free, talloc will just
Yeah.
it'll abort the whole CTDB. So
but we don't actually do a double free.
Yeah. Because CTDB doesn't crash, so
Yeah. There's a whole bunch of stuff there that we've just swept under the carpet because otherwise it would take 10 minutes or 15 minutes instead of 5 to explain that we ended up with a pointer pointing to the same value it pointed to before. It was just mind-blowing. Okay, we have this feature in CTDB called NAT Gateway, and I won't explain that because that will take 5 minutes. But basically, in most cases, what it does for us is it adds a last chance default route on a node, so it can route out data via another node that actually has an external connection. So here's what we want to see, and we've got that default route with really 10 minutes? We will have time to sing songs. This is fantastic. Did you memorize the CTDB song?
Yes.
Good. Okay. So we've got this fallback route with metric 10 to do all the good stuff for us, but it's missing. So the first thing we do is we check the configuration. Is NAT Gateway set up correctly? I've seen a lot of situations where NAT Gateway is misconfigured. It's fine. Is the script that actually adds the routes being run? Yeah, we add an echo foobar to the script, do what we need to do to make it run, foobar in the logs. It's being run. What happens if we trace it? Well, here's an IP route add command, and it looks exactly like what we want. So, we do a set -x in our script. Beautiful. We see this. And it's right. What could be going wrong? So at this stage we get interactive via instant chat. No access to the console. So somebody runs the route command, the IP route add command. We want to see if there's a silent failure. No silent failure. Because I'm thinking, there's got to be a bug in the IP route command. As you'll see, there is. But IP route show. Did the route get added? It did. Okay, there's no bug in the IP route command. Which IP command are we running here? sbin IP. Perfect. This is good. Show me all the IP commands, please. sbin IP, bin IP. Now, those of you who are Debian lovers are sitting there going, that's fine. Bin IP is a symlink to sbin IP, so your system is a good one. This is Red Hat Enterprise Linux. There is no bin IP. Two nodes of the cluster have got an empty but executable bin IP command. See, you thought this was going to be some deep CTDB bug. This is one of the most surprising things I have ever seen, you know.
Did you ever figure out where it came from?
No. Why does the script do something else? Well, because somebody, thank you, somebody decided, well, we better make sure the path is set correctly, and added a path setting to the include function for the scripts, which does things in a different order. Now, not only is this completely unnecessary, but once we started doing the interactive debugging, it cost us 5 or 10 minutes because, you know, why can we run the command, but the scripts are doing somewhere else? So I think this is an example of don't do that. The big question is, why is anything in the scripts working at all? You know, there are IP addresses on the interfaces. Well, okay. The things that matter were using absolute paths. Now, at some stage later, I removed every absolute path in the scripts so that we could replace them by stubs when we're testing. You know, you write your own IP command as a shell script. So there's the answer. The fixes. You want to see the fix, don't you? There it is, yes. And the other one is, as I said, don't set path because you'll confuse yourself if you're debugging. Now, I think we've got questions. That means we won't get to do the last one, yes?
Sorry, I just wanted to ask, wouldn't exec fail to execute a zero command?
No. It works like a charm. It's the equivalent of bin true. In fact, I used to think it was funny, on a Solaris system, bin true used to be an empty script with a copyright header. That was lovely. Do we still have, I'll answer questions, yep.
Just want to say, how did MTB go?
How did it get there? It had been there for 2 years. No further comment. No idea. No idea. Yes?
Did you make your use of paths consistent in the script, so you're always using SMIP in the script?
No path set anymore. We'll just use the system path so that if you do something interactive on the command line, it's completely consistent with what the scripts would do. Tridge, uh-oh.
Is there a CTDB song?
Is there a CTDB song? With apologies to AC/DC, CTDB, it's dynamite. This talk sponsored by IBM Legal. And I think we've had so many questions. We have 1 minute? We can take more questions, or we can try to cover the last spare bug in 1 minute. Spare bug. Crap. Okay, the log is full of repeated messages and monitoring hasn't been run for days. We get this in the logs on some node every second. We also see that monitoring event has been cancelled. That's bad. That means if Samba goes away or an interface goes away or somebody pulls out a network cable, we don't notice. In this case, monitoring hasn't been run for days. And the first question is, has there been time travel? No. So what's generating all of these IP reallocated events? Okay, normally this would be the recovery master node because it does all the IP management stuff. But we go there, we look in the logs, there's nothing special. It's doing this too, but there's nothing special. So we look somewhere else and we see this idea that there's some IP address on an interface, but CTDB has forgotten about it. Or maybe it's been put there by somebody who added an empty bin IP command. And we see this every second. And this is what's triggering the stuff on all the nodes. So first question is, why doesn't CTDB know about the address? Is it misconfiguration? That's what we first thought. We thought one of the admin utilities might be botching this. The answer is no. If CTDB recognises the problem, why doesn't it fix it instead of going like that? Okay, so we were sitting there staring at this, and Ronnie Thalberg was still working with us, and he was sitting behind us, and I'm going through the log. We're going up and down through the logs, and suddenly he goes, "Stop, go back." And he noticed that there was a release IP, which takes an IP off an interface, shortly followed by a take IP. So here's the code. The first thing we do is we launch the scripts, and then when the callback gets called, it disassociates the interface from the IP address. No, disassociates the interface from the IP address. Then a take IP associates an interface with the IP address and then runs the scripts. The ordering of this is actually quite useful for other reasons, but that's pretty straightforward. Good things happen. What happens if the order of events is very slightly different? Slightly. First of all, we launch the scripts to remove the IP from the interface and do all the other housekeeping, and we register the callback. Then we disassociate the interface from the IP address. Sorry, then we associate the interface with the IP address. Then we disassociate it. Then we run the scripts to add it, and there it is on the interface. It's a pretty simple bug. And there's a simple workaround here. If you do notice this happening, instead of saying, I don't have a record of what interface this IP address is, you ask the operating system and you try to remove it. That's nice and straightforward. And there are some other fixes. You know, there's a big hammer. You put in a lock, basically. When you're running one of these things and another one comes in, you just go, no, go away. There's already one happening. So you can't do a release, a partial release, and then have a take intervene. And the other thing is, of course, in the release IP callback, you have a look and you say, hey, operating system, is this IP address on an interface somewhere? And if it says yes, you go, oops, and you return an error. So we've done a couple of fixes there. Do I have to go back? This talk, courtesy of IBM Legal. Questions? Thank you.